So I was talking about reduced sequestration in roots. Uh, uh, because when they are sequestering in the root cells, it means that there is a less translocation toward the shoot, so which is required for the phytoremediation. So the phytoremediating plant must have less sequestration in the root cells and more sequestration in the shoot cells. Uh, Biofortification, then the ground part, that is the low bioavailability in soil. So in that case, of course, the biofortified plant must have ability to secrete some compounds which can enhance the bioavailability of those minerals which are present in the soil. Uh, Intercropping of FE strategies and 1 and 2 plant species. So if we intercrop the plants with both strategies, so they can help each other for the iron remobilization. Soil condition can be modified by chelators can be used to enhance the uptake. And then fertilization of trace elements, of course, that is also biofortification. But in case of phytoremediation, the first part, that is okay, modification of soil pH, use of metal chelators, but these chelators may also be source of contaminant. So we have to enhance the bioavailability, but if we are using again the chelators which we were using here uh, in the biofortification, so if we use that in bulk for phytoremediation, so they may also be one source of contamination. So that must be cared of again. Enhance rhizosphere microbial activity to improve the metal solubility. Microbes can be utilized to enhance the bioavailability of the metals in that soil. Assess feasibility and relative risk of phytoxide to phytostabilize. Uh, because if we have very high concentration of contaminant in the soil, so it's not wise to extract it, rather wise to phytostabilize it. Because if we are first thing is that we will have very few species which can grow at that concentration, and the second, if we get it that into the shoot, so then we have to dispose of somewhere, so that will again be an issue. So the best way is that if we can phytostabilize them at the same place, then that can be helpful. So what can be offered for biofortification through phytoremediation? Uh, if we correlate it with each other, so can phytoremediation plants become source of human micronutrients elements? So that I mentioned that if we are growing plants to remediate the zinc and iron content from the soil, and the use of those plants in the bioenergy production, and the ash can be utilized for as a fertilizer. Even the fresh plants, they can also be utilized in those places where we have a deficiency of those elements, because we know that in acidic soil we have a high concentration of zinc and iron, and then in alkaline we have less. So the plants used for phytoremediation in acidic soil can be utilized in alkaline soil for the biofortification. But again, there are limitations, of course, to transport that biomass. But if they are being used as a bioenergy material, so the ash can easily be transported relatively. Managing toxic metals in plant tissues. Uh, that can help us because when we are biofortifying using different transporters in the plant species, so they may also have some impact on the uptake of toxic metals. For example, if we are working to enhance the uptake of zinc in a plant species, so then that may have enhanced uptake of cadmium, of mean the similar metal atoms. So if it's so, then that is not a very good for the biofortification. So how to manage that? So fire remediation can help in that case. Of course, future research is required to further to correlate and interrelate phytoremediation and biofortification. So conclusively, biofortification, this is just a sum up of what we have discussed today. Enhancing trace element bioavailability in the rhizosphere, translocation from root to shoot, redistribution towards grain tissue. But in phytoremediation, hyperaccumulation traits with high biomass production, more contaminated soils, phytostabilization may be the only feasible option in more contaminated soils. So as I mentioned in the last slides. However, understanding of the underlying mechanism for ion acquisition, transport, and homeostasis in plants may be helpful for the both cases. Further, cadmium, iron, zinc, and calcium may share the same transporter as essential elements. So in that case, we have to take care of the toxic metal uptake when we work for biofortification. So that was all about today.